for this one, you can see that this, you can rewrite this as 1/2 mv squared plus 1/2 ky squared. If you differentiate this with respect to time, chain rule gives you ky times 2, 2 cancels the half, and then dy dt. That's exactly what we have up here. So chain rule differentiating gets you back to here. This is the total mechanical energy, ignoring the friction term, right? So this is like sort of energy in a sense. I mean, it is the total mechanical energy if you think of the mechanical energy being stored either kinetically or in the spring, right? And then there's this spoiler, the friction term over here, right? And this is what? For B positive, this is always what? Always negative, right? So this explicitly tells you that dE dt for a damped system, the change in energy per time, is minus bv squared. So it's kind of fun. You can think about phase planes, right? You can go back to, for example, we talked about how this was the Poincare plot. Those are supposed to close. Sorry. The Poincare plot, like this is y versus v for a simple harmonic oscillator, right? If b is equal to 0, you get the purple thing, right? Energy is constant. The solutions to the equation are constant in energy, and they just go on and on. They oscillate back and forth, right? But when you add friction to the mix, you lose energy. And you can actually qualitatively, all right, kind of picture this. So what it means, right, if you have friction, let me draw it in green, is you're starting here, right? And okay, the rules are still the same. If velocity is positive, I'm going this way, right? But what happens as time goes on, you're losing energy, right? You're going to lower and lower energy curves. So after you start losing energy, you lose energy. You keep going to lower and lower energy curves. So let's do something like this. And you can think about that. And you can create, from the hypothetical conservative case, you can create the non-conservative case by just imagining toggling from the conservative energy levels down, 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 down. So ellipses become spirals. And of course, that's actually what happens in real physical systems, right? They don't stay energy you start with. They lose energy and they all spiral to 0 usually. This stuff is done systematically in like chapter 9 of your text. I don't expect you to study that just yet. I'll assign homework on it later in the course. We'll test it more formally then. So at the moment, you're just responsible for like showing that this relation holds, or that the energy is constant, like we worked out the other day. Like those two derivations, I'd like you to understand, and I'd like you to be able to use it like the Armageddon problem, right? All right. Any questions? So this is why we have physics as a prerequisite for this course, so that when I tell you these things, they make a little bit more sense than they would otherwise, right? Ay, ay, ay. Okay, so I have 2 specific problems in mind I wanted to work for you guys. Oh my goodness. I see I have talked too much. So let me explain briefly. I'll try to make it simple. So suppose you have a y prime plus y equal to f of t, and f of t is equal to 1. For t less than or equal to 1, and it's equal to t for t greater than or equal to 1. So this is a piecewise problem. So here's how you solve this. Let me give you the game plan, because I assigned you one of these in the homework. 1, solve for t less than or equal to 1. 2, solve for t greater than or equal to 1. And I think I need to give you more data, right? To keep things really simple in here, we're going to assume that y of 0 is equal to y prime of 0 is equal to 0. Actually, I'm not sure that makes it super simple, but it's just what I'm choosing. So the idea is here, we're going to solve it for t less than or equal to 1. We're going to solve it for t greater than or equal to 1, right? And since the initial, here we'll impose the initial conditions, right? You impose the initial conditions wherever they're given. And then how do you get to the next case? Solve for t. You join to case 1 via continuity. All right, so I'm a little short on time, so I'm just going to take off the gloves and do it. You got y is c1 cosine t plus c2 sine t. The particular solution for 1 plus 1. This is the general solution for t less than or equal to 1. You can try it out. If you take y prime prime plus y, you'll get back 1. So you see my particular solution works. Yes? And it's got sines and cosines because we got lambda squared plus 1 is 0. So that means lambda is plus or minus I. So that's my homogeneous solution. I apply the initial conditions, right? Y of 0, c1 plus 1 equal to 0. Therefore, c1 is minus 1. Y prime of 0 is c2 cosine of 0, which is 1. So that's equal to 0. So therefore, c2 is equal to 0. So consequently, y of t is equal to minus cosine of t plus 1 for t less than or equal to 1. So stage 1 is done. Now to solve for, how about t greater than 1? To solve for t greater than 1, I have to solve y prime prime plus y equals to t, where y of 1 and y prime of 1, or whatever we're forced to have them be from this, right? So let's see here, y of 1 is what? 1 minus cosine of 1, right? What's y prime of 1? Just sine of 1, right? So those are my basically gluing conditions. Those will make the derivative and the function match up at 1. So I need to solve this, right? But again, this one's sufficiently simple that I personally can just write it down. You might need to do some work, that's cool. I'm not saying that you should be able to do this, I'm just saying that I happen to be able to. Plus t. Partly because I think I did this one before with somebody in here. You can check that t is a particular solution, right? Y prime prime, 0 for t. Y is t. T equals t. Woohoo. Yay. And then y of 1, c1 cosine 1 plus c2 sine 1 plus 1 is equal to 1 minus. And by the way, to be clear, I should put some bars in these or something. These are not the same c1 and c2 as we had before, all right? These are new c1, c2, just to be clear. And so what do you got here? You got an equation. And then what's y prime of 1? Minus c1 bar sine of 1 plus c2 bar cosine of 1 plus plus 1, actually, as it happens here. And that's supposed to be equal to sine of 1. Let's see here. So that gives me cosine of 1 times c1 bar plus the sine of 1 times c2 bar is equal to minus the cosine of 1. And let's see here. Minus the sine of 1 times c1 bar plus the cosine of 1 times c2 bar is equal to sine of 1 minus 1. Two equations, two unknowns. Got to solve them. Right? Can you solve them? Cosine of 1 is not 0? No, no. Sine 1 and cosine 1 are both ugly. Ugly, ugly. I'll tell you what I would do. I multiply the first one by sine 1. And I multiply the second one by cosine 1. And then you know what I do? I will add these equations. Don't tell the other math professors I wrote that. And then these cancel. Sine squared plus cosine squared, woohoo, 1. So we get c2 bar, these cancel, is minus cosine of 1. Yeehaw. I don't know, woot. Pick your favorite expression. So there's one of them, and then you can go back and find the other one, right? So there's a problem in your homework that's case-wise defined, right? You have like a spring mass system, and it tells you the force is one thing one time and another thing different time, and it changes at one point, right? This is the kind of way you want to solve it. It's really two problems that you have to paste together in the middle. This is a pain, isn't it? Yeah. It'd be nice if we had some kind of slick method that would do all of this at once through one sweeping calculation, you know? Anyway, it would be nice. Laplace transforms. Anyway, yes, eventually we'll learn that we can do this all at once with Laplace transforms, but one thing at a time, right? So it's good to go through what we're doing here before we do that. The other thing I was going to do for you guys was I wanted to work out something like, like x squared y prime prime plus xy prime plus 3y equals to, I don't know, something e to the x or something like that, and see if I could solve it, with variation of parameters. But I don't know, maybe we'll do it next time. What is next time? Tuesday. Then what happens? Fall break, right? And then test. Yeah. So you need to be trying to sort of wrap things up conceptually for yourself. Basically, next class, I don't really have anything. I probably won't even do that next class. Next class, I probably just talk about the totality of the course, everything we've done. Next class is really a review. But it's not, when I do reviews in here, it's not like I'm not trying to just like prep you for the test necessarily. I'm really just here for your questions. So left to my own devices, I might do that. And you don't want me to do that because that may or may not be relevant, right? What you'd rather do is ask me educated questions about, the nooks and crannies of the annihilator method or whatever it is that still doesn't quite gel for you. Okay? If you'd like, guys, next time we could spend like 30 minutes of it with you trying to work through an old test, and then we can take like the last 40 minutes talking about the solution to it. I think that would be a good format for you guys. there wouldn't be enough time to do the problems. It would be like frustrating. I'm not going to grade it. Just would that be good? I can do that if you'd like that. I think I'll try that out and see if that works for you guys. So next class we'll spend a good bit of time with you just trying to do some problems, and then we'll talk about their solutions. So anyway, thanks. I'll shut up. See you. Have a good weekend, I guess. Maybe when I come back I won't be coughing. Ha 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 ha.